So in this lecture we are going to talk about the torsion formula. We'll derive the torsion formula and see what it is, and we'll discuss other aspects of it. So we have already discussed the idea of internal torque in circular bars. So we are usually interested in the stresses developed by these torques, so that we can better study, analyze and predict the behavior of circular members. For example, if you have in vehicles you have wheels and shafts. So the engine transmits the torque to the wheel, and the shaft of the wheel is usually subjected to high torque. So let's say we would like to find out what are the stresses developed within the shaft due to the torque. So when it comes to properties of material, we know that we don't usually have a quantity named limiting torque or ultimate torque, but we do have quantities like ultimate stress, which is a quantity that represents the strength of the material. So the torque which a shaft can withstand depend on the several quantities, the design parameters of the shaft. If shaft is very thick, if it has a large radius, it can take large torques. If it is made of a good material, it can take larger torque. So it depends on material properties and design parameters. But stress is a quantity which is mostly related with the material property. So we would like to so for example, if you are designing a shaft with certain type of material for a certain radius, let's say we would like to calculate what is the torque the shaft can take. To make sure that the shaft does not fail, to make sure a safe design of the shaft, we like to choose a certain material and radius of the shaft. So for such purposes, we would like to come up with a relationship between the internal torque and the stresses it sets up in these shaft members. So we are also interested in tubular bars, which means that they have an empty space inside. So to come up with such a formula, which we call torsion formula, we will have to use some assumptions. So the assumption number one is that, so we will use a few assumptions, 3 assumptions to be precise. The first one is that a plane section of the material, okay, I think it's better to it's better to use a so I've instead of writing this down, I've got this text now. So there are three major assumptions we use for the derivation. The first one is that the plane section of the material perpendicular to the axis of the circular member remains plane even after torques are applied. So if you have such a circular member, take a plane which is perpendicular to the axis of the circular member. Which is the axis of the circular member? This one. So take any plane perpendicular to the axis of circular members and it remains plane even after torques are applied. Even after torque, even if there is a twist of the member, there is no warpage, there is no distortion, and these planes remains as planes. So obviously if it gets deformed, some of the basic assumptions and simplifications will not be followed, and we don't want it that way. Now the second important assumption is that when the member is subjected to torque, shear strains vary linearly from central axis reaching gamma max at the periphery. So let's say okay, the shear strain at the center is 0. You can see that so shear strain can assume to be the angle shown here in radians, which is something you, let's say you have a if you are applying force on such a member, such an object, what will be the shear strain here? So if these angles are small enough, you can you will see that this angle is actually equal to the strain, the linear strain, shear strain. So that is how shear strain is defined. So here in this case you can see that O1, O3 is lying on the axis of the member, and it remains that way even if torque is applied. There is no angle here, so that tau value is, shear strain gamma is 0 at the center, and at the outer surface you can see that CD, which was the original location of let's consider this plane O3CD01. So after torques are applied, this member got twisted a little bit. Now CD reaches the position CD dash. So D moves from D to D dash. So an angle here, DC D dash, this angle here is the shear strain. So that shear strain is maximum at the outer surface and it is 0 at the axis. So you can see, even if you apply torque, O1 O3 doesn't get affected. So that is this angle here is 0 and this angle here is maximum at the outer surface. So this is the assumption here. A circular member subjected to torque, shear strain gamma vary linearly from central axis and reaching gamma max at the periphery, maximum strain at the periphery. So the third assumption is that we are talking about linearly elastic material. That's simple and straightforward. We are assuming that Hooke's law applies and we are not going to talk about non-linear materials. So what does that mean? It means that shear stress is proportional to the shear strain. So if shear stress is proportional to shear strain, just the way we have already told that shear strain is varying from 0 to maximum from center to the outer periphery. Now if shear stress is proportional to shear strain, shear stress will also be varying from 0 to maximum to the periphery. One more important thing is that that variation is linear. Shear strains are varying linearly from 0 to maximum. Since the shear stress is proportional to shear strain, shear stress will also be varying from 0 to maximum linearly, since Hooke's law applies. So these are the three important things you need to keep in mind when you are doing the derivation. A plane section remains plane section. A plane section perpendicular to the axis of the circular member remains a plane section even after torques are applied. Shear strain vary linearly from central axis to periphery, reaching maximum value at the outer surface. And we are talking about linear elastic materials, which mean Hooke's law applies. So stress is proportional to strain, shear stress is proportional to shear strain, hence shear stress varies just the way shear strain vary. These are the assumptions involved. Now let's start the derivation. So the process is very simple. There is not much to do here. Let's simply take a shapes. Let's take a cross section of the circular member. Now we have already assumed that shear strain is varying linearly from maximum from central axis to outer surface. So shear stress is also varying from 0 to maximum. From central axis to outer surface. So this maximum value here, we will call it tau max. So if you take so this is shear stress is 0 here, tau max here. In between, if we choose a point which is at a distance rho from axis, what will be the, at this point, what will be the shear stress? Shear stress is varying from 0 to tau max so linearly. So obviously that should be if the, let's say the radius of the circular member here is C, so shear stress at any point should be rho by C into tau max, right? So when rho is this is the linear variation, right? When rho is 0, 0 into tau max 0, tau is 0 when rho is 0. When rho becomes C, when rho is equal to the radius of the member, then C and C gets cancelled, tau is equal to tau max. So this linear variation of rho makes sure that tau is also varying linearly. So this is basically this equation is basically the third assumption we used, nothing else. So this is the this is what we do. Now let's simply do the derivation. What should be, let's say this is the cross section of like I've let's simply choose an area, a small infinitesimally small area dA, and let's say the internal torque resultant here is T. An external torque T is applied, and because of that there is an internal torque resultant T. This is the torque here, and we know that torque is equal to how do you find out torque? Torque is the moment of force. So if we find out torque on the member due to force applied on dA and integrate it throughout the member, we will get the total torque, right? So first we will find out force on member A, force on member A, and we'll multiply it with what? Let's just say rho. Here is the, here also I have taken rho. Rho is a variable, okay. Rho is the distance between dA and the axis. So about axis, force on A multiplied by rho will be the torque due to force on dA. So that should be integrated throughout the area. So this is the torque due to this due to the force on this small elemental area dA, and if you integrate it throughout the area you get the total torque. So what is the force here? We know that at a distance rho from the center, the stress, shear stress is actually tau. The value of shear stress is tau. So the force on that elemental area will be equal to shear stress multiplied by area, right, which is dA. So the shear stress tau multiplied by area dA will be the force on that area, and that multiplied by rho integrated throughout area A. Now we know that this tau is linearly varying from 0 to maximum, and using the third assumption we know that tau is equal to, we will substitute tau with this equation here. So tau can be substituted here, so rho by C tau max into rho into dA. Okay. Now what can we do? We can take out C, which is tau max, and tau max is a constant here, it can be taken out. C is the radius of the circular member, it can be taken out. Inside what remains? Rho into rho square dA. So integral rho square dA throughout the area will be the term remaining here. And what is that? What is integral rho square dA? It is the polar moment of inertia of a circular area, right? Polar moment of inertia let's call it J. Polar moment of inertia of a circular area is essentially not circular area, any area is defined as integral rho square dA throughout the area A. So we can use the formula there. And that quantity for a circle, what is the formula for polar moment of inertia? J is equal to pi d raised to 4 by, if you remember it, you learned it in your previous semesters or classes. So that is pi d raised to 4 by 32. But however we will use the we will use J for polar moment of inertia. So this quantity is called polar moment of inertia, that is tau max into J divided by C.
Today you are going to submit this one BTech question, engineering graphics.
Yes, all right. This formula we have come up with let's so the quantity that we are usually looking for is tau max, the maximum shear stress. So the maximum shear stress a material can withstand is usually the limiting parameter that usually designers look for. So we will write the equation in terms of tau max. So tau max is equal to maximum shear stress is equal to Tc divided by J, where T is the torque, C is the radius of the circular member, and J is the polar moment of inertia. So this equation, that equation is known as torsion formula. And the derivation, like I've shown here, it's very simple and straightforward. Once you make three assumptions, and when you come up with when you assume a linear variation of tau, you just find out the torque by integrating this equation, which is nothing but, you know that torque is moment of force, and multiply force in the elemental area with corresponding radius and integrate it throughout the area. So within a few steps you will arrive in the torsion formula. So this is the formula for tau max, and you can also calculate tau at any point using this formula, right? Tau max can be calculated using Tc by J. Once you have tau max, you can substitute tau max here and find out tau at any point. That is also possible. So this formula is known as torsion formula. We will stop this lecture here.